Hello, everyone. Come on in. Glad you first to make it again, Lindley. Ask any questions if you have them. Of course, I'm not quite ready to start, but because there's only you here. But feel free to ask me questions if you're ready. All right, got another student. Woohoo! Hey, Jacob. Ask me any questions if you have them. It's only 2:01, but only two of you are in here, so ain't much we can start yet. Of course, we'll have to start whether people are here or not in a few minutes if no one shows up. Since our lab this morning, I posted a bunch of stuff. Hopefully, it's you know what it is, but it's basically I've got a series of photos of the vernier calipers making measurements. Like I think there's 5 photos of one measurement, and there will be a little discussion board heading for that one. I haven't posted my reply yet, which is where the actual answer will be. The main thing is your job is to try to look at those photographs and predict what that measurement is. When I actually do my discussion, I'm going to walk you through exactly all the processes I go through to come up with that reading. And the answer will be, quite a ways down. So even if you accidentally look at it, hopefully you won't give yourself the answer immediately, because really a big part of doing problems and doing things like measuring with the vernier caliper is your ability to come up with your own reading before someone gives you a reading. In other words, it's a lot easier and not helpful to actually make it fit, make someone else's reading fit into your mind. Whereas making yourself use your mind to figure out a measurement and then compare it to an existing measurement is a learning process that actually helps you. So make sure you do that. Then there's another one, again, another discussion board with another series of photos. And that one's a complicated measurement where basically it's hard to tell whether the 0 hash mark on the sliding scale is exactly lined up with a hash mark on the main scale, or if it's slightly to the left, or if it's slightly to the right. And that's always a trick. It's always a tricky thing to measure. So I wanted to belabor that quite a bit in that answer. So I showed you, made arguments about what it would be if it was to the left, what it would be if it was to the right, and of course the obvious is what it would be if it was actually directly on it. Even though I didn't actually discuss that, I should know that it's going to be that digit and then nothing but zeros after it. But I went through that process, and hopefully that'll help you as well. Then I also put a couple photos in there that you're supposed to look at and make readings yourself, and those are part of your lab for this week. So you're actually going to turn in those answers for your lab this week. And I've already put up the turn-in link so that you'll know exactly what you're supposed to do, because it says it in there. It's got a photograph of the paper that I wrote up. Plus, it's got some other photos and descriptions of what you're supposed to do with them. And it's got a link, of course, where you turn it in. So that's what's due for lab this week. Of course, it's not due until the beginning of lab next week, which would be 9 a.m. on Monday. So anybody have any questions about that? Let me go for a second, see if I can find the screen that I want to share and then show it to you so we'll all know what we're talking about, since I'm just saying all this stuff here. Maybe that's it. Yeah, that's it. Okay. So I want to share the screen, and we're going to look at our Canvas page so you'll know what I'm talking about here. All right, another person's entered the room, so that's helpful. So what I'm looking at is the wrong course. That's helpful. That is super helpful. Let's look at this course. That's not it. That's better, but not it either. Better, but not it either. Which one I'm just looking at? What happened? No. Okay. Let's go to this one then. No. Let's go to this one. Okay. So I'm going to go to modules. Now I have to scroll all the way down. So we're in week 11. So what you'll see is one, there's the link to the Zoom meeting that we're currently in. There's a photograph of the veneer manual. There's a photograph of veneer caliper, sort of focusing in on the parts. And here's veneer caliper, a part zoomed in on a little bit more. Then I made a discussion where you can discuss amongst yourselves what's the distance, what is the distance, that's a typo, what is the distance measured in the photos below. Let me fix that right now because it aggravates me. I changed the wording of the question and forgot to remove a newly extraneous word. The other one's going to have the same thing because I copied it in there. And then I have a series of 6 pictures here for you to actually see the veneer. And I'm using those pictures so you can understand basically the process I go through when I measure it, and also the process of how you actually look at the reading and make sense of it. I think it's trying to download now. Okay, so you look here. I did not try to download that. If you look here, that 0 hash mark is where the measurement's supposed to be. And we see that this is 1. And of course, remember we counted 1, 2, 3, 4, 5 spaces, 6, 7, 8, 9, 10 spaces between 0 and 1. So each of these is 1/10 of a centimeter. The fact that that 5 is there, it's a little bit longer than these, but not as long as that. That tells you it's a half. So you don't have to, if you're doing this one or this one, you can start counting from here, 5, 6, 7. Here we see that we're past the 1.5, we're past 1.6, and we're past, not quite to the 1.7. So you know it's 1.5 something. That's the way you go about reading veneer calipers to get your first decimal place, is you just find out where the 0 hash mark on the on the sliding scale is. And when you find out that hash mark where it is, you say, what's the last number that it's passed? If it was, for instance, somewhere between this mark and this mark, it'd be 1.5 something. If it was between this mark, or excuse me, yeah, this mark right here, this mark and this mark, so it's in the space here, then that'd be 0.9 something. Here it would be 0.0 something. So keep that in mind. This is 0.0. This is 0.1. This is 0.2, 0.3, 0.4, 0.5, 0.6. Now, in this case, it's past the 1.6, so you know it's 1.6 something. And then you go about looking for which ones of these line up. Now, you see it looks, in this case, it's like a little bit more than half. So I expect it to be around the 5, 6, 7 area. It doesn't look so much like 5, 6, or 7 are lining up at all, but I'm getting parallax. Notice the center of the photo is right over the 0 hash mark. So this is not a good photo, nor is it a good way to look at the veneer caliper when you're trying to make the measurement. Once you get that first digit, you should use that, of course, use this vision where the 0 is in the center of your vision. That's the point of view you want to make. But once you get that first decimal place, then you're going to move your eye along so that it's always looking perpendicular to the surface and find which one of these lines up best. So that's why I took the series of photos. So you can see, okay, I've gotten the 1.5 something or 1.6 something. I think that's what I found was 1.6 something. And now I want to look at the other photos and try to figure out what's the measurement that I want to make. Is it in the 5 area? Is it in the 6 area? Is it in the 0.7 area? Or actually, I should say 0.5, 0.05, 0.06, or 0.07 area. So remember, we had 1.6, if I remember correctly. So here's me centering up more or less on the 4.5. I don't see anything lining up very straight there. So that's not it. Would next go and center up over the 5, say, and look and see if any of those center up. Then I look over the 5.5 to see if any of those center up. And then I look, or actually, I should be looking at these. Sorry. I look right here. The center of the photo is like 5.5. So I should be looking around here. It doesn't look like any of those line up. Then I'll try and centering up on the 6 and see if any of those line up. And then I try 6.5, seeing if any of those line up. That looks like it's closer to me. Or look over at 7 and see if those line up. And that looks pretty close to me too. So I'm thinking it's somewhere between here and here. So then I, of course, did you the great favor of taking yet another photograph, which is a really big deal because there's a buttload of data to email to yourself. And I will now look at photo 3. And you can see this is me. The center of the photo is roughly along the 4.9 area or the 4.8 area. Remember, these are excuse me, 6.6 or 6.8 area. Forget that I'm reading when you don't see the whole thing, it's real easy to slip into reading this instead. So it's really down here. It's 6.2, 6.4, 6.6, 6.8. So we're talking 1.660, 1.62, 1.664, 1.668, or excuse me, 1.66 or 6.8 there, so on and so forth. That's really what the measurements we're talking about, assuming my language, assuming I was paying enough attention to my language. The green thing is this is a 6, this is a 6.2, 6.4, 6.6, 6.8. It looks right there that like that 6.8 lines up pretty well, but it also looks like that 7.0 lines up pretty well as well. But again, I'm not necessarily dead center on that. So it's kind of one of those things you need to be careful about. And if you were just holding the veneer caliper, you just look at it over and over and over again. But in our case, we're looking at photographs, which luckily I was just kind enough to take the photographs centered up on all the important areas. So ultimately what I found out was this is the most important area. And it looked to me like these guys were really, really close to each other. So that's where I'm trying to read. This is 7. This would be 1.676, 1.678, 1.680. Somewhere in there is what we're trying to read. Anyway, so that's what I did in the little bit of a brief break we had between lab and my next lecture. So I did that. I put all that stuff up there, but you can see it in our module 11 for week 11. You see first off again the Zoom links, the manual plus photographs of just the device, so you can compare it to the photos of the parts and that the manual tells you. Here's one measurement that's supposed to be an easy measurement to make, but I took a great deal of pains to take all the photographs. I haven't written up the solution yet, which will be in here. And then I did write up this solution because this was the hardest one. And this is a veneer scale where I read between 0.5 and 1.0. In other words, that's all the answer I'm giving you, because I wanted you to realize that, hey, if you're not past that 1, the first digit is going to be a 0 for the whole number part. Okay. So here's the lab that I gave you last time. But we didn't do anything with that this time, just in case you need to follow up on what it was. This is an erroneous thing. It's not supposed to be there. And here's your homework for this week. So any questions on that, everyone? I just thought of something. I might need to go back and check this out, but I think it's good. Yeah, it should be good. Yeah, that's right. I was mixing it up because there was one I wanted to do where I took an image of the veneer caliper. Let me stop sharing just a second. There's one I wanted to do, I just mentioned it a second ago, where I wanted you to consider what would happen, but I didn't do an example like it. I thought about it and I just didn't do it. But if you'll notice on the veneer caliper, once I separate like that just a little bit, say between the 0 on the main scale and the first hash mark on the other scale, okay, see if I can zoom into that. Notice the 0 down here on the sliding scale is actually between the 0 hash mark on the main scale and the first hash mark after it. If that was the case, then your first digit would be 0.0. I was going to take a point and make a point to show you a drawing, a measurement like that, but I didn't do it. And that's what I was getting a little confused of what I was talking about earlier. So that's just something that's important that you should know. Hey, if the digits pass the 0, but not to the first scale, to the first hash mark on the main scale, then you know the first digit and the first decimal place are 0.0. Okay. Anyway, so like I said, I didn't do that photo, so I've just verbally given you the information, so hopefully that'll help. All right, now we're going into chapter 31, and chapter 31 is sort of a recap of Maxwell's equations. Not only that, it's a correction to Maxwell's equation, because it turns out this is the part that Maxwell contributed. Not only did Maxwell take Michael Faraday's notes and more or less convert them to mathematical forms, which I've told you before didn't turn out very well because he ended up using quaternions, and he also used the potentials instead of the fields. And all of that made it really, really cumbersome, and a lot of people just didn't really take him seriously. One, because he wasn't a first wrangler, and two, because it was mathematically esoteric. So a lot of people just said, I'm not putting my time into that. I understand stuff pretty well just from what we've read from the documentation. So there's no sense in doing that. But along comes Oliver Heaviside and creates more or less in whole cloth by himself vector calculus. I think the other guy's name was Stephen Gibbs. I might be wrong on the first name, but I even might be wrong on the last name, but I'm pretty sure it was him. It's the guy that's the Gibbs free energy, where that came from, which is an American. So I know the guy was an American. I just can't remember if it was Gibbs or not, and I think it was. So anyways, those two guys come along and repurpose or rewrite, if you will, Maxwell's equation into vector calculus form, and they are sort of the disciples. Well, actually, it's Gibbs isn't necessarily a disciple, but Oliver Heaviside and some friends of his, some people he meets, are the disciples for Maxwell, in the sense that they propagate the usefulness of Maxwell's equations. But as I said, Maxwell wrote those equations in a form that wasn't very useful. But one thing he did do, in addition to just writing them from Maxwell's notes, or excuse me, from Faraday's notes, which were contributions not only just of Faraday, but also what he learned from other people. But he was able to just translate that to mathematics and write out his equations. But there was one part he added, and it turned out that Ampere's law was a little short. So Ampere's law was missing something, and it was Maxwell that figured that out. So that's the first thing we're going to discuss. So let me give you an idea of what I mean by that. I do have my iPad charged up this time, so we're going to say, yay, Mr. Younger, you did your job. And I'm going to say, yeah, I'm amazing that way. I do my job 5 out of 10 times correctly. Anyways, here we go. So we have Maxwell's equation, which is really, really, really useful. So let me give you a short introduction to what Maxwell's equations are, just because we've learned them already. The first one we learned, of course, was Gauss's law. Notice Coulomb's law is not one of Maxwell's equations, but Gauss's law is, in fact, the closed integral of E dot dA is equal to Q enclosed over epsilon naught. That's Gauss's law. Again, which I've told you before, it's Gauss's law, not Gauss's helpful hint that sometimes works. It's just a matter of the way we use it in this class is we use it to solve for the integrand E, which is a very perverse thing to do with a mathematical equation in general. Normally, we have a differential equation and we solve it by doing something analogous to integrating or something equivalent to integrating, or we have an integral equation and we integrate things. This is an integral equation where we're actually sort of solving for the integrand. It's kind of weird. Or we have algebraic equations and we're solving a particular variable. Now we have that. We also have the next law we covered, which was Ampere's law, or excuse me, the next law we covered, which was Faraday's law. And Faraday's law said closed integral. Actually, it wasn't closed, was it? Let me see, Faraday's law. Yeah, it was closed. I didn't write it in this way. That's why I didn't remember. But one version of it is Ampere's law is the closed integral of E dot, I'm saying Ampere's law, sorry. One of the versions of Faraday's law that I didn't really write but once is the closed integral of E dot dl is equal to the negative, and you could put an N here, d phi. Now, in this case, we found that it was the magnetic flux that was changing over dt. So that phi b is the magnetic flux. What we wrote it as before and used it most of the time before with was this EMF equals negative N times d phi b over dt. That was the form we normally used. But what we're telling you is the electric potential difference is actually equal to the voltage, of course, and voltage is negative integral v dot dl and that sort of thing. So that's another form. And this is called Faraday's law. Okay. Now, there's a law we didn't cover at all, and it's actually more closely related to Gauss's law, but we'll talk about that one in a second. So the next thing I want to do is the one that we did cover, which is Ampere's law, and that was the closed integral of B dot GL is equal to mu 0 times I enclosed. Now, just looking at these three equations, can you guys guess what might actually be missing? See, we've got two equations for the electric field, but we only have one for the magnetic field. What kind of equation or what kind of thing on the left-hand side of the missing equation do you expect to have?
Probably an integral of some sort.
That's a good start. Yes. So all of these are integrals. So you'd expect that. What's the difference between the two different E electric field integrals?
One's per length and one's per area. So do we need a volume?
Well, we've got, let's just say you're thinking right in terms of what's missing from, say, E, because there's length, there's volume, there's area, that sort of thing. But what if I tell you that the electric field equations are complete? What's missing is a magnetic field equation. What would you say is missing now? Remember, there was an integral stated, and I agreed that that was correct. So we know that part's missing. I would tell you, since we're saying it's about the magnetic field, I'll definitely tell you that B is missing. What's next?
Would it be dA?
Exactly. And it turns out, this is like Gauss's law for magnetic fields. It turns out it's 0. And another way we can refer to it as is there are no magnetic monopoles. It's harder to see in this integral form what I'm talking about here, but you sort of can still see it. If you look at Gauss's law, the reason that's not 0 is because a point charge can create a bunch of electric field lines that point radially outward and don't have any pointing in, right? So you can encompass that charge inside of a spherical volume, say, and then the flux is all positive. It's all coming out of through the surface from inside to outside. And that's what happens when you have a single charge that in this case is positive. Well, in the case of magnetism, you have one charge that's normal, one charge that's normal, and one charge that's north and one charge that's south. And again, I'm putting quotation marks around it because it's not really a charge. But if you had a isolated N, you would expect a B dot dA not being equal to 0 because you could have all these field lines, say, leaving the north pole, going radially outward, and all of them would be completely positive, piercing the surface of the sphere that you centered on it, going from inside to outside, and would give you a positive quantity. However, what we find is that doesn't exist. So for every north pole, you have a south pole. So just as many lines leaving the north has to re-enter the south, so that whatever surface you try to center it within is always going to have an equal number of charges going out as it has charges going in. So that's why that fourth equation, Gauss's law for the magnetic field, also says there are no magnetic monopoles. Okay, so that's the state of Maxwell's equations as we know them right now. Now, the problem is I'm going to have to put this in quotation marks here, specifically because it's not quite correct. And why is it not quite correct? Well, the way Ampere's law works is just like the way Faraday's law works, is you are going to do a integral over a line segment, and it has to be a complete closed line segment. In other words, it's got to be a line that starts somewhere and ends at the exact same spot. So you're going to integrate in a path from one point back to that exact same path. That's what the circle means on the Faraday's law. It's a closed circle. And the DL means it's a path or line or circle integral, if you will. And the same thing with the B dot DL, that's a path integral or a line integral around a closed path, okay? Now the deal is the current on the right-hand side of Ampere's law and the N d phi B dt on the right-hand side of Faraday's law, those are supposed to be quantities, flux, for instance, in Faraday's law, piercing any surface that's bounded by that path. So if you imagine, for instance, a path, no matter what its path is, so I just drew an arbitrary path, for instance, and you say integrate in this particular direction, which is sort of a counterclockwise, any surface that could be bound by that actual path is a fair surface to imagine. So for instance, we could imagine taking a piece of, let's say, plastic, using a 3D printer. We could print out a flat version of this path, right? And then we could take that flat version of this path and we could put a little handle on it. So we could put like a little, let's say a little handle so we could easily hold it like this, right? So there's our little handle. Now I'm going to take that thing and put it in a little vat of water, glycerin, and dish detergent. Anybody know what that stuff makes? Water, glycerin, and dish detergent. Small amount of dish detergent, but even smaller amount of glycerin and a buttload of water.
Soap?
Yeah, it makes sort of a soapy water substance. Have you ever done anything like that with that stuff when you were a kid? This is the part.
Not that I remember.
You probably have. That's the most people don't know. Us nerds know because we're nerds. But basically, that's the way you make bubbles. Okay, so if I took that loop that I just made and laid it in that bubble surface, that bubble solution, and then lifted it out, it would actually make a pretty nice flat plane that is bound, meaning its ends on that loop. That's what it would look like, right? But any surface you could make with whatever concoction of glycerin, dish detergent, and water you do. For instance, some things need really sharp turns, and if it's got really sharp turns in it, then you're going to have to let up the glycerin amount a little bit. If it's got mostly smooth and slow turns, you could use less glycerin. But if you imagine all the different shapes that could come and be bounded by that, then that's all the different things through which N times d phi dt could be calculated, or through which the current could go through in the case of Ampere's law. So there's one of the surfaces. Another surface might be just like this, which is sort of the same shape as the outside, but it's also got sort of a bend to it like this. So you can imagine sort of all these different shapes of surfaces that could be bound by this loop. Does that make sense? Well, that might be kind of esoteric for you. So let me bring it into something a little more straightforward. And this thing that's a little more straightforward is, let's imagine a wire coming from the left. And then it runs off, of course, into a plate like this. And then a little distance away is another plate. And then out comes another wire. Okay. So we could have a current going through here, and then we could have a Amperian loop, say, like this. And of course, if the current is going this way, we'd want our Amperian loop to be integrated around this way. Let me make it obvious what's the front and what's the back here. Okay. So what we're seeing is this loop is coming out of the page and then going back behind the page back here. So it's actually in the right directions to do the closed integral of b dot dl is equal to mu 0 I enclosed, right? Everybody sees that? And that's perfect for this surface right here, that sort of the flat bubble surface. But what if the flat bubble surface was not the surface being bound by the actual loop? What if the surface being bound by the actual loop was sort of like a potato sack that went around like this? Sort of looking like a fat tick, if you will. And in fact, would have some shape this way through here. And then, of course, some shapes like this way around here. Can y'all visualize that three-dimensional shape? It's like a sack.
I think so, yeah.
Yeah, so that's another shape that's perfectly fair. However, that's inside of a capacitor, and we know that current doesn't pass through a capacitor. It does something like passing through a capacitor, but it doesn't, because really what happens is charges build up on the left-hand side, positive charges, and then those positive charges compel the positive charges in the right-hand side to run away, and no charges actually go from the left plate to the right plate, so there's literally no charges going through the sack. Since there's no charges going through the sack, there's technically no current going through the sack surface. And that would say the closed integral of b dot dl would equal 0, because mu is actually 0. Mu going, we call it enclosed because it went through the center of the loop. But in fact, anything piercing the surface bound by that loop is fair game. So in that case of the sack that I have drawn here, none of those actual charges went through that sack. So we would actually get an incorrect response, because it would say the magnetic field 0, even though we're measuring out there where there is a current. So that was the problem that Maxwell saw. So Maxwell had to fix it. So this is how fixed Ampere's law. This was bad. This part right here was really bad, and he had to fix it. So what he did was he said, okay, well, what I want is something like I. So and you might mean, that might mean something, oops, with units of coulombs per second, which equals amps. So we said, okay, well, Q for a capacitor, which is what we were talking about, is of course given by, remember, C equals Q over V. Yes, go ahead, Jacob. Is that, let me check it. Might be that he's, Jacob has a comment he posted in chat that I didn't see.
Oh, no, sorry, I forgot to unmute. So if we're doing a SAC, that would be a three-dimensional object, right? Wouldn't we be doing the surface integral of B dot dA?
You can do, remember, a surface has not only an area, but it also has, you know, lines along it. For instance, if you sewed up a potato sack, there could be a single string that went from the top left of the opening all the way down around the bottom and then back up to the top right of the opening. That one string is a path on that surface. So you can have both paths as well as areas on a surface. And it turns out that the actual differential equations that these integral equations came from were things that were done either over surfaces or out of surfaces and around lines and stuff like that. The one that creates Ampere's law is actually a cross product that is encompassed in a curve. So the left-hand side of Ampere's law is actually a line integral as opposed to a surface integral.
Okay.
But that's good thinking. You're doing exactly the right thing. You're realizing that Maxwell's equations have stuff where they do stuff on areas and they have stuff where they do stuff on paths. But it's just that every time we dealt with a surface, we used an area. But that doesn't mean that's the only thing you can do when you're dealing with a surface. In fact, you can do a line too in this case. So that's what we did. It's basically curl versus divergence. You talk about things diverging or converging into a volume, and those equations make Gauss's law and Gauss's law for magnetic fields. And then you talk about things curling, say, not necessarily out of a volume, but over a surface. And you can detect that curling that's going over on a surface by measuring things around the edges of that surface. And that's what Ampere's law and Faraday's law gives us. Okay. All right. So yeah, that's exactly the kind of question you should ask, but it's also exactly the kind of question that you're not supposed to be required to understand yet, just because you haven't covered not only the full breadth of vector calculus, but also not differential equations, because this is the ugly of all ugly differential equations. All right, so we know that I has units of coulombs per second, and I just wrote an equation for charge. So if I could take the derivative of that with respect to time, then I'd get units of actual amps. So what I postulated was that the charge for a capacitor is the capacitance times the voltage. And if we just take as a model, let's consider the parallel plate capacitor. Well, that parallel plate capacitor has a capacitance of epsilon 0 A over D. But that voltage for the parallel plate capacitor happens to be equal to the electric field times the D. Again, what we mean by this is when we're talking about capacitors, actually I should draw it this way. When we're talking about capacitors, there's an area A and there's a separation D. So that's what that A and that D is, okay? So now if I want something with units of current, then I can take dq capacitor over dt, and I would get, first I'm going to multiply them, and then I'll take the derivative. So notice when I multiply them, this d cancels out with that d. So I'm going to take the derivative of a constant. I shouldn't have done that color. Shouldn't have done that color either. Of a constant times an area times an electric field. Okay, that's what I'm going to take the derivative of. That constant, of course, is just a constant, so that's going to be epsilon 0. But does A times E, does that look like anything we've seen before? An area times the field?
Kind of looks like Gauss's law.
Yeah, what is the left-hand side of the Gauss's law called? which is by necessity equals to the right-hand side. But anybody remember what that F word was?
Field.
Close. It had an L in it, just like field did. Flux. Yeah, remember flux is the integral of A. Yeah, what the flux? Yeah, flux is an integral of A dot or E dot dA, right? So let's take a little leap and assume that it's not going to be epsilon 0 A times the derivative of E with respect to T, but in fact, epsilon 0 D magnetic, or it was magnetic flux before, but now we're doing the electric flux, not to be confused with the electric slide. So this is our postulated current that maybe exists or should exist according to what Maxwell was seeing. So Maxwell said, well, it looks like we still need something over there because there's no current going through that stupid capacitor, but that surface is certainly a fair approximation that we could use. So I've got to have something go through it. Well, what I do know is that the capacitor has an electric field, and that has a flux, and this stuff right here looks like it has the right units. Then I remembered that Ampere's law said the closed integral of B dot dl is equal to mu 0 times I enclosed. So it was actually mu 0 times something with the units of current. So obviously this is going to have to be mu 0 epsilon 0 d phi dt. If, I mean, from a unit standpoint, this would be acceptable, right? Now all that's left is experimentation and physics investigation to see whether this equation is right. But guess what? It is. Okay. Even though, again, just like when we found that U is equal to epsilon 0 E squared, and when we found that U is equal to, or excuse me, over 2, and we found that U is equal to 1 over 2 mu 0 B squared. Even though we found those theoretically using a capacitor in the first case and a solenoid in the second case, they turned out to have exactly the right answers. That's the same thing that happened here. We used a capacitor as a model example, and it gave us exactly the right answer that works in all cases. So Ampere's law is now, and there's a couple of ways you can write it. You can say the closed integral of B dot dl. Notice that's a magnetic, doesn't turn out to be a flux. It turns out to be from a magnetic curl over a surface, is equal to mu 0 times I enclosed plus what they called this quantity over here, the epsilon 0 d phi dt, was something called I displacement. Now, that theory that gave them the idea of using the word displacement has been discarded. That hypothesis doesn't really work anymore, but we still call the term the displacement current. Okay. It just doesn't fit. Like, it's really hard to try to find a way to use the word displacement to make sense of the quantity epsilon 0 d phi E over dt. So that's the derivative of the electric flux with respect to time. Now, if we look at Maxwell's equations again, let's group them in a little better order this time. I'm going to say the closed integral of E dot dA, that's the electric flux, is equal to Q enclosed by the surface divided by epsilon naught. And we now have another one, which is the closed integral of E dot dl. We already had this already, so I should have said now. I'm just trying to group the electric field equations together. Well, this is Faraday's law, and it turns out to be negative n d phi b over dt. And now we have the equation that I just introduced, not just now, but before that, a closed integral of B dot dA is equal to 0. And that says there's no magnetic monopoles. Okay. And we now have from Faraday's law, the closed integral of B dot dl is equal to mu 0 I enclosed plus mu 0 epsilon 0 d phi E, notice it's an E instead of a B, dt. Now, believe it or not, this kind of bothered me when first time I heard it said too, but see how much more similar Ampere's law and Faraday's law is. Now, I saw it as a difference because that stupid mu 0 I enclosed made me think I needed another term up in Faraday's law, but we don't need that. Okay. So what makes them so similar is their development in time. Notice there's only one thing dealing with time, a time ordered derivative in both of those equations. And that's the derivative with respect to time of the magnetic flux in the case of E dot dl and the electric flux in the case of B dot dl. So this tells us a symmetry of nature that is really amazing and awesome. A changing magnetic flux will create a voltage, which is Faraday's law, right? And therefore a current. And a changing electric flux will create a magnetic field, which of course is also due to a current. So an electromotive force creates a current, and that can be created by having a changing magnetic flux. But a magnetic field is created by a current or by a changing electric flux. So it makes just a whole different kind of symmetry. And these are Maxwell's equations. And as a bare minimum, every student of this course and any course thereafter dealing with electricity and magnetism should be able to state them immediately. In fact, that was the very first question on the very first exam I had in grad school. And in fact, it was in one of my courses, it was the very first question on the very first test, or actually the very second test that I had in undergraduate electrodynamics. Is state Maxwell's equations and their names. And in grad school, it said state Maxwell's equations and their names and give the boundary conditions that those equations suggest. So in other words, there's a boundary conditions that occur as a result of these equations. And it basically says that the electric field component perpendicular to a surface is continuous unless there's a surface charge, and the component parallel to the surface is always continuous. The magnetic field component parallel to a surface is continuous unless there's a surface current density, and the magnetic field perpendicular to a surface is always continuous. That's what you can actually get from these four equations if you just take away the actual sources. In other words, you get rid of Q enclosed and you get rid of I enclosed in the differential form of the equation. Now, this one in the top left is called Gauss's law. So I'm just going to write Gauss here just so we can keep track. This one in the top right is called, anybody recall?
Faraday,
very good. And bottom left?
Gauss's law for magnetism.
Mm-hmm. Or you can say no monopoles. And what about the right one?
Ampere.
Ampere. So I don't expect you guys to know all those cool boundary conditions I just gave you, but I definitely expect you guys to know these: Gauss's law, Faraday's law, Gauss's law, and Ampere's law, and, you know, of course, be able to state them. That's certainly a fair thing. So we've come somewhere. We've come a long way. Just since chapter 21, we've now established all four of Maxwell's equations, and they can be used this way. They're quite nice, in fact. They can be used this way. And in fact, they can also be used in their the way that I'm used to, which is in a way which we call it differential equations. These, believe it or not, come from a differential equation, and your book takes the time to derive basically a wave equation from it, which is really, really tricky and smart the way they do it. It's a tricky thing to pull off, by using the vector form, or excuse me, the integral forms of these equations, but it's really beautiful to watch it work. It's a lot easier if you actually do it with the differential equation form. So let me show you just for a second. I'm going to share my screen with you, and I'm going to go to my YouTube channel. So let's stop this share. And I'm going to go to my YouTube channel and share that. So let me say share this screen. And I'm on my YouTube channel, sort of. I'm on my YouTube. Darn it, I want to be on my YouTube channel. I'm actually in the belly where you build stuff and fix stuff. By the way, that your video from this lab this morning will be there as well. I just hadn't posted it yet because it takes more time than I had between lab and my next class to upload. And if I would have started doing it, it would have made the internet really, really slow. So I'm going to do a search for Maxwell. Actually, I'll do a search for wave. No, Maxwell's probably a better one. So let's see what comes up with it. Maxwell's wave equations in the SI. Okay. So this is a way you can actually figure out how to derive Maxwell's equations. I'm going to fast forward to about here for a second. Now, this is back before I started using iPad, so a lot of these videos back then were that stuff. As a permittivity of free space. We also know that del cross E, that's Gauss's law, that first one, is equal to negative partial of B with respect to T. And again, this is in the SI system of units, and this one's called Gauss's law. And I'm going to label it equation 1. And this one's called this one is called Faraday's law. And I'm going to label it equation 2. And then there's another similar equation for the magnetic field, and that's del dot B, the divergence of B, is actually equal to 0. That's sort of Gauss's law for magnetic fields, and it basically shows that there's no magnetic monopoles. That's why we always have a magnet when it's broken two is going to make it into 2 magnets as opposed to 1 north pole, 1 south pole. And then we have Ampere's law, and Ampere's law is del cross B is equal to mu 0 J plus epsilon 0 partial of E with respect to T, and that's called the displacement current that Maxwell had to introduce to make his equations. Okay, that was a bad place to pause. Let's move my hand out of the way. Put my hand out of the way. Okay, so that first one, top left there, is Gauss's law, and that's in differential equation form. So remember that del operator, I've talked to you about that before. It's basically a vector written as I hat times the partial derivative with respect to X, not operating on anything, not differentiating anything yet, because it's an operator. It's not given what it's put in there to do. It's just the thing before it acts on something. So I'd say leave it a space and say plus J hat partial derivative with respect to Y, again, acting on nothing, plus K hat partial with respect to Z, again, not acting on anything. Now, that's it in Cartesian coordinates, and you very rarely want to use Cartesian coordinates in electricity and magnetism because, as you can see, all the fields, if you try to find lines of equal field strength, they're almost all spherical or cylindrical or something like that. So spherical coordinates and cylindrical coordinates is a much better coordinate system to use, but the equation or the operator in those coordinate systems is ugly. Really horrible. But the main thing is what you see here is something called a divergence. And if you integrate a divergence over a volume, that means you're going to take an electric field and you're going to imagine extended over some volume. Okay. Maybe we take a sphere. That's a very good space, a very good volume to use. We'll take a sphere centered on the origin. Okay. And we're going to calculate the divergence. That means, like, you think divergence and convergence as stuff leaving or coming in. We're going to calculate the amount of stuff diverging or leaving the surface. So you can literally just keep track of everything that pierces the surface of that sphere. And what we find is that quantity is going to be equal to the charge density within that sphere divided by epsilon naught. So that's what that rho is, the charge density per unit volume. So if I integrate this del dot E over a volume dV, then I have to do the same thing to the right-hand side. But what happens when I integrate rho dV? What do I get?
It would be.
Y'all
Sorry,
got
go on
it, yeah.
ahead.
So if it's in units of charge per unit area,
The rho is charge per unit volume, and the dV is units of volume.
yeah.
So you'd just be left with charge.
Exactly,
Yeah.
which I thought what y'all were trying to say. So that's why Gauss's law says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. Now you see where the Q enclosed over epsilon naught comes in. What you don't see is the integral over a volume of the divergence doesn't give you a del dot E. In fact, there's a theorem. Anybody know the name of this theorem? I suspect Ryan and Trey, you might.
Theorem for what? I'm sorry.
There's a theorem that talks about the divergence, the integral of a divergence over a volume. There's a Stokes theorem, a Green's theorem, and go ahead.
Gauss's theorem. They call it so many different things.
Yeah, there's a bunch of different things, but basically the generalized version is whatever you have leaving something is equal to whatever goes out through its boundary. So that's the general statement, right?
Is it
In this
Green's
case,
theorem?
What? Yeah, there you go.
Nice.
In this
Okay.
case, you have a divergence over a volume, and therefore you have that integral of a divergence over a volume is equal to the amount leaving the surface. And if you want to count the amount leaving the surface, that's the flux. Does that make sense? Remember, flux is the integral of E dot dA.
Sorry, can you say that one more time?
Okay, so the left-hand side is the integral of the divergence over a volume. Remember, the divergence is how much is leaving the volume. And there's a general rule that says if something leaves an area or a volume, the amount that left is exactly equal to the amount that went through its boundary. In this case, we're talking about a volume, so the amount that leaves the volume is exactly equal to the amount that went through the surface boundary, the surface area, right? So do you see that the amount of the electric field leaving a volume is exactly what we call the electric flux?
I think so, yeah.
Yeah, that's what happens. So using that generalized Stokes theorem, Green theorem, whatever, actually not Green's theorem, generalized Gauss's theorem, generalized Stokes theorem, or whatever, using that, we find that the divergence over a volume is equal to the flux over the surface. That's why the left-hand side becomes the closed integral of E dot dA. It has to be closed because it has to enclose a volume, and that also dictates which way is positive and negative. And it's already equal to the other side because we found that the other side was the integral of rho dV, which is Q. So it's Q enclosed over epsilon naught. So that's where the version of Gauss's law that we use came from. Does that make sense to anyone? I'm trying to explain this without the math, but with all the concepts as much as possible so that y'all can have a better understanding than I got when I took this class. So that's one version. And of course, that would also mean the equation to the right of del dot E equals rho over epsilon naught. It's going to get the integral of B dot dA is equal to 0, just like the integral of E dot dA is equal to Q over, or excuse me, is equal to Q over epsilon naught. So that's how you make equation 1 into the integral form of Gauss's law. Equation 2, on the other hand, is a little different, but it's I think you'll see more this more in line with the Stokes equation. So if you integrate, for instance, the left-hand side and the right-hand side over a surface area, this left-hand side of equation 2 is called the curl of E. And the curl is sort of how much it tends to rotate around to any particular spot in space. So if you have a electric field line that points this way, and then you go over here and it points this way, and then you go over here and it points this way, that looks like it's tending to rotate around. Whereas if it looked this way, and then this way, and then this, that doesn't make any sense at all. If it went this way, and this way, and this way, that wouldn't make any sense at all. In other words, you wouldn't expect it to have any curl in either one of those cases. But if you see it going like this, and then this, and then this, and then this, that looks like something with curl, right? So if you calculate the curl over a surface, that would be the integral of del cross E. And that's it. Del cross is a vector because it's a cross product. So you dot that with a dA, a surface area, okay? And then, of course, if you do that to the left-hand side, you got to do that to the right-hand side, and that becomes the negative integral of the partial of B with respect to T, and B would be dotted with dA as well, a dA vector, an area vector. Well, if you pull that, and there's a whole process to do this in advanced calculus where you can take that derivative and pull it outside of the integral. And instead of it being a partial derivative, it's going to have to become a regular derivative. So you're going to get on the right-hand side of equation E, del cross E, equation 3. On the right-hand side, you're going to get negative derivative with respect to time of the integral of B dot dA. What's the integral of B dot dA? So now,
wouldn't it just be BA?
Wait a second. There's this. Take my hint. You're thinking right, but it's an F word again.
Flux.
There you go. See, it's the magnetic flux in this case, right? So that's yeah, what it is. So that's the process that you're missing in going from the integral equation to the vector equation, I mean, to the differential equation. So let me write that down real quick, just so you get an idea. So we had del dot E is equal to rho over epsilon naught. That's going to become the integral.
Oh, change the perspective because we can't see.
Thank
this.
you.
Yeah.
Thank you. I was just getting ready to say, man, y'all are slow. Y'all not getting this at all on the screen. And I was like, yeah, that's me, because I didn't switch the screen. Thanks, Ryan. Okay. So now we should have it coming up. Let's see. Yeah, there it is. So del dot E is equal to rho over epsilon naught. That's the differential form. What I chose to do was take a integral over that over some volume, and in fact you could do over all space if you wanted to, but notice the dot product is in fact a scalar, so I'm just going to multiply it by dv. But if I do that to one side, I got to do it to the other side. The epsilon 0 obviously can come out front, and we get the integral of rho dv, which you guys were wise enough to realize was, what's the integral of rho dv?
Charge.
Yep. And since it's the same volume enclosed by the volume on the left, it's clearly the Q enclosed. So the left-hand side, by that generalized Stokes theorem, remember, whatever goes through a surface or whatever leaves a volume has to go through the surface. That's the fundamental rule. And you can write it with these fancy derivatives and integrals and formulas and all you want, but that's just the rule. Obviously, space has a hole in it. The universe has a hole in it if that's not true. That's why the Stokes theorem has to be true. So the left-hand side of that just becomes the integral of E dot dA, because the flux is how you calculate what's leaving a volume through a surface. And that's equal to Q enclosed over epsilon naught. We have a similar result, del dot B, but I'm going to skip that and go to the other part. Del cross E is equal to, I'm going to leave off the n right now. I'm going to say that's equal to d phi B over dt. I'm going to integrate both sides over an area this time, though. So I'm going to say the integral of del cross E, which is a vector quantity, by the way, dotted with dA, which is another vector quantity. It's a unit area, though, is equal to, again, like I told you before, I can actually pull out a derivative from under the integral. And, oh, excuse me, I shouldn't have written it that derivative that way. Actually, I'll leave it as is. And I'll use my eraser. Okay, I can pull that derivative out and make it a exact regular derivative instead of a partial derivative. But what I have to do first is I want to say, dang it, I forgot to change it from eraser, is equal to negative integral of partial of b with respect to t dotted with dA again, like that. Now, in this case, we can see that if I pull the derivative out, it's going to become a regular derivative. But what is left is the integral of b dot dA. What's the integral of b dot dA?
Magnetic flux.
Exactly. So now we've got one more version for this particular equation. And that by Stokes' theorem, that curl over a surface becomes the line integral of the boundary line. So that becomes the integral of E dot dl is equal to negative d by dt of the integral of b dot dA. Actually, I don't want to write it that small, so I'm going to go ahead and write it as the flux like it is. And let's fix my handwriting by pretending I've got a really fine pen here. Let's fix this T down there because that looks like crap too. I don't like that T still. So that's the new version and or excuse me, that's the old version that we already had in integral form. And now you can see to some extent, like I said, I haven't given you all the math, but I've given you the physics and the concepts behind the math in such a way that I hope you can now understand it. And you could probably see, for instance, that del dot B, because of what del dot B is up there, you can probably see that del dot B is going to be equal to 0 here. And you'd be exactly correct in saying that. And you could also see that del cross B, this part might be a little difficult for you, but del cross B, you can probably suspect, since the del cross B became integral of E dot dl, the del cross E that is. So you can probably suspect that del cross E is going to become something similar on the right. Well, we had dB dt on the right for the del cross E, whereas the b dot dl, we have mu 0 I. So you're probably going to suspect something that's going to be integrated over a surface. So in fact, it's going to be the integral over the surface of J gives you the actual current. So that's how you could make the I. And then the other part is mu 0 epsilon 0. Those are just constants. They got to be there. But we know that that came out to be the actual flux. So this, in fact, must be just like the flux before just became the derivative of the flux. Now we're probably going to get d electric flux, or excuse me, in this case, yeah, it will be electric flux over dt. Okay.
What is J?
J, we actually covered that before, believe it or not. It's actually the current density. I, the current, is equal to the integral of J dot dA.
Okay, I remember.
All right. That's all that is. Oh, why did I do that for? Stupid me. Notice I just copied the flux instead of the actual electric field, or instead of the actual magnetic field or electric field in this case. And I also made it a regular derivative instead of a partial derivative. So it's supposed to be the partial derivative of E with respect to t. And I think that's supposed to be b, isn't it? No, that's right. Okay. So anyways, that's the new version of Maxwell's equation. But if you look at that video that I actually pulled up, let me swap share. Now, if I go back to that same video that we were looking at, I actually go through the derivation of Maxwell's, or excuse me, of the wave equation using Maxwell's equation. What I'm going to do is just show you the end result of that. You can actually look at this and see the actual calculus going on to get there. It's actually, you use a couple identities. Let's see where I'm at now. Use a couple identities and you'll get something that's starting to look like a wave equation already. But that's the general version right there. See that I have that operator del, this time it's squared. So it's del dot del, which means the second partial with respect to x squared plus the second partial with respect to z, y squared plus the second partial with respect to z squared. But it's a scalar because I did a dot product. Well, that acting on the vector e is equal to 1 over all this junk squared times the partial of e with respect to t. That's the classic wave equation. A second order derivative in space is equal to 1 over a velocity squared times the second derivative in time. That's the very quintessence, if you will, of a of a wave equation. And this happens to be a vector wave equation. And that is a derivation of it that's nice and neat and a lot less, I think, a lot less confusing on a physical scale than what Giancoli does. But I'm going to do Giancoli. I just wanted to make sure you guys saw this and you might find it a little easier to deal with. Now, the whole reason of all this, doing this, is I wanted you to have an understanding of what the electric field is, or excuse me, what electromagnetic radiation is. So that's going to bring me to the next page. So let me stop sharing again and go back to my iPad. Anybody have any questions so far? We haven't done anything that you can actually solve too many problems on so far, and that's okay. Well, so really the point here was to give you an understanding of what Maxwell's equations say and why they work the way they do, okay? Now I'm going to give you something where we can start to make some use. So if we imagine a wave equation in one dimension, which is really impossible, you would just have a first order or second order derivative of something with respect to position x. You know, so it'd be the second order derivative of e with respect to x squared. And that's equal to 1 over velocity squared times the second order derivative of e with respect to time squared. That's not really the way it works too well. And in fact, when we actually do this, what we find is we get del squared e is equal to 1 over c squared, because it turns out that quantity down there is actually the speed of light, and that's how Maxwell knew that he had discovered what light was. Okay, now what this left-hand side means, so I can get the vectorness out of it, the vector calculusness out of it, it's the second order of derivative of ex with respect to t plus the second order of ey with, I said t, that's not supposed to be t, stupid me, that's the other side, of x squared plus y squared plus the second order derivative of z, ez with respect to z squared is equal to 1 over c squared times the second order of e with respect to, this is ex, of course. I should actually write this as, ooh, I left off an I hat, j hat, and a k hat. Ex I hat plus ey j hat plus ez k hat. Let me make this a little prettier. So that's the actual wave equation. And it turns out there's another one just like it for for B. Maybe not write it that way at all. I can make the analogy a little better by saying That's sort of like what's going on here. So what Maxwell was able to figure out, and you can put this together just by using Maxwell's differential form of his equations too, without looking back at this wave equation. You can find some fundamental properties, specifically that E is perpendicular to B, and that E is perpendicular to the velocity, and that B is perpendicular to the velocity. And in fact, that E cross B is parallel to the velocity. Just by using Maxwell's equations, you can figure out that. So we're left with this problem, or this neat explanation, if you will. So let's imagine this is the velocity. Now, what I'm going to say is we're going to have a electric field that's oscillating. Like this, so that this is the electric field at this particular point in space. This is the electric field at another point in space, and this is it at another point, and this is it at another point, and this is it at another point, and this is it at another point. And then in addition to that, there's going to be a magnetic field, which I'm going to draw the same size, but you'll see from this that it's not really possible to be the same size, at least not in the units we use. And what this says is the electric field points this way at this spot, this way at this spot, this way at this spot. And I think you can see if you use your right hand rule and lay, say, your pinky finger, or let's do it the other way where we do our fingers like this. And the first vector is your index finger, the second vector is your middle finger, and your third vector, the result of the cross product, for instance, is your thumb. So if I put my finger in my index finger, if I point it in the direction of E, which is straight up, and I put my middle finger to the left, which is the direction the magnetic field is at that point, then you see that the velocity, in fact, points out at me. And that's exactly what this shows. And this is what electromagnetic radiation. So this is what we call EMR, electromagnetic radiation. Radiation. And the nature of it is that all types of it travel at the same speed. V equals C equals 299,700, and I'm trying to remember this digit right. I think it's 792,458 meters per second exactly. It's defined that way now, so I'll put a 0 with a bar over it. All these things of electromagnetic radiation all travel at the same speed. And there's a really good or really nerdy mnemonic that I use for remembering the parts of the electromagnetic spectrum, which is another word we put on here. And you can have the verbal version of this. I think, Atreyu, you might have actually put it in the transcripts. Did you ask for the transcripts to be recorded on this one, Atreyu? I didn't see it.
No, that's all right.
Now might be a good time because
to.
I'm getting ready to write down a mnemonic. So go ahead and do that real quick and I'll approve it. And I'm going to give you a mnemonic that I won't have to write sentence form wise. So,
all right, got it.
Was a big fan of Rush Limbaugh until he died. I hated almost everything his positions he held, and he aggravated me a lot of times, but I loved listening to him. And he always complained about us teachers being basically communist, pinko liberals or whatever. And I'm not going to say I'm a Democrat, but I'm going to say that I am a teacher. And because of that, I come up with this mnemonic, and it's great excess undermines various industries, Marxism rules. I'm going to repeat it again. Great excess, notice the weird spelling I did of excess. Great excess undermines various industries. Marxism rules. That's the parts of the electromagnetic spectrum. Anybody want to take a guess what G is? Incredible.
Gamma.
Yes, yes, like the Incredible Hulk. X.
X-rays.
Yep. U.
Ultraviolet.
Yep, I got a sunburn. How about V?
It's the violet and ultra.
yeah, it's Roy G. Biv, but in this case, it happens to be Vib Gior, and that runs from about 300 nanometers to 700 nanometers, 350 to 750, say. Okay, and then I, keep your eyes warm. Yep, infrared. How about hot pockets for M? Microwave. And R?
Radio
waves, exactly. So all of those things are radiation of the type electromagnetic radiation, and they all therefore travel at the speed of light. And the kindergarten version of the wave equation is velocity is equal to frequency times wavelength. So that's another thing that'll come in handy, but we'll call it a day at that because we're at the 3:21 mark, which is a minute overtime.
So I stands for infrared?
Yes, sir, infrared.
And then R just radiation.
Radio, like radio.
Radio. Okay.
Yeah. And in fact, the numbers on your radio stations, at least if you're listening to FM, corresponds to the frequency in megahertz. And in the AM corresponds to the frequency in kilohertz. So that will come in handy. Okay, you guys are free to go. I'll wait for the last person to leave in case you have any questions. But thanks for coming. And I'm sorry I couldn't be with you there instead of being here. But I need some time. And it's nice seeing you guys. Thanks for showing up. And I will see you on Wednesday.
I really like the conceptual explanations, by the way. That really helped me understand a lot of it.
Cool.
Yeah.
I'm glad to hear it.
Cool. See you around.
Thank you.
Hey, I had a quick question about lab report, Professor.
Yes, sir.
Hey, so it just opened up this morning. Am I correct in tracking that?
The lab report from 2 weeks ago, the optics one?
Yes, sir. Yeah.
Yeah, I hadn't posted the actual link for you to turn it in. I had made it last week when Ryan reminded me, but I forgot to publish it then. So this morning I set that up. So you now have until midnight tonight to put that in without having any late points taken away.
Okay. Well, my question was, I mean, obviously curveball class isn't in person, but I have the lab report done, but I don't have the pictures that my lab partners took of our sketches. Can I still submit it? And then next week when we're in person, submit the pictures of our lens refraction and diffraction?
Yeah, that shouldn't be a problem. And in fact, if you get it beforehand, do, but it's not a big deal. Submit it when you do. And actually, it'll probably be there at least before I grade it. And as long as that happens, I won't even take points off.
Okay. Thank you so much.
No problem. Anyone else? That seems like it. All right. I'm going to say stop share. And it looks like, yes, everybody's gone. Have a good day.